ARMA colleagues. It's very pleasure to bring you a new series of ARMA Future Leader webinar series. This time we invited Dr. Tianyang Guo to bring us this very interesting topic, the effect of microstructure on the cracking mechanism and the acoustic emission features of rocks. Dr. Tianyang Guo is a postdoc scholar at Stanford University. He holds a PhD from Hong Kong University, where he focuses on rock mechanics. He earns bachelor and master degrees in geotechnical engineering from Wuhan University, China. Before joining Stanford, he was a postdoc fellow at the Hong Kong Polytechnic University under the PolyU Distinguished Postdoc Fellowship 2021. Dr. Guo is an experimentalist and a data scientist, specializing in rock mechanics and engineering geology. He has an interdisciplinary background and is skilled in integrating methods from rock mechanics, geophysics, geology, and artificial intelligence. He applies these techniques to tackle scientific challenges in rock mechanics, particularly those relevant to net zero initiatives, such as enhanced geothermal system nuclear waste geological disposal and CO2 geological storage. Dr. Guo has been an active contributor to rock mechanics and the rock physics community. He's serving as the session chairs for both the 58th and the 59th ARMA annual meeting and a governor for American Geophysical Union for meeting in 2024. Okay, now let's give time to Dr. Guo.
Okay, so thank you, Chichuan, for a kind introduction. And so thank you all of you to come to listen to my presentation. So it's my great honor to contribute to the ARMA Future Leader webinar. So today, I would like to talk about this topic, the effects of microstructure on the cracking mechanisms and acoustic emission features. So this presentation will consist of the two parts. The first part will focus on how the microstructure will affect the cracking mechanisms. So in the second part, I would like to mention something about the intelligent acoustic emission monitoring. So as we know that, so many geoenergy applications involve injecting the fluid in the subsurface. So for instance, in the enhanced geothermal system, so EGS, the water will inject to improve the permeability of the geothermal reservoir and to transfer the geothermal energy back to the surface. So in the CO2 geological storage and the enhanced oil recovery, the CO2 will be injected in the subsurface to boost the oil production or to securely store the CO2 deep underground. So one of the significant objectives or the consequence of injecting the fluid is to creating the fractures within the rock formation. So taking the EGS as example, the geothermal energy is stored in the deep underground in the rocks such as granite. However, the challenge is that the permeability of the geothermal reservoir is relatively low, and we may not able to collect the heated water and the steam from the production wells. So we have to use the hydraulic fracture to create the cracks in the reservoir. So the process begins with the use of the perforating guns to create some initial cracks in the rock, and then the high pressure water is injected to further fracture the formations. So this hydraulic fraction will interact with the natural cracks and create connected fracture networks. So such a network is very important for achieving a high surface area to volume ratio, and also to ensure that we have the sufficient flow rate so that we can sustain the energy production for several years. So as you can see that the characterizing the crack formation, this crack network is important for optimizing and maintaining the productivities of the geothermal reservoir. However, we cannot directly see the cracks underground because the rock are not transparent, right? So we have to rely on some indirect information such as the microseismicity to understand the fracture networks. So for example, in Utah fault, apart from the injection wire and production wall, we have full seismic monitoring wire. So when we do the hydraulic fraction, the microseismicity induced by the cracks can be monitored. So however, the challenge is that it's often difficult to infer the cracking behavior from the microseismic data, given the complex condition in the field, such as the stress condition and also the lithology of the rock. So to deal with these challenges, we as experimentalists could make use of the control experimental task to correlate the cracking behavior with the lab scale seismicity or the acoustic emission under different loading conditions. So the relationship between the fracture and the AE data could be used to interpret the microseismicity in the field. And also to deal with the, before we go in deeper in the cracking behavior of rock in geoengineering, so let's take a moment to revisit the fundamental of the fracture mechanics and how they inform us about cracking process in rock. So according to the linear elastic fracture mechanics, the stress will become infinite when it approaches the crack. However, the rock cannot sustain the infinite stress. So when the stress exceeds the strength, and it will have some micro cracks, and the fracture process zone will form in front of a crack tip. So as we can see that the fracture process zone sometimes appear as the white patches in some rocks like marble. So to describe the development of fracture process zone, the Hogland proposed a conception model, and as you can see that in the upper part of this figure is the different stages of a crack initiation and the propagation, and the lower part is the low versus displacement of behavior of the rock sample in the fracture test. So as the low increases, the pre-existing microcracks and also together, and the stress-induced microcracks together form a fraction process zone. And when the crack density increased to a critical value, a new the fraction process zone will fully development. And then the macroscopic cracks will initiate and propagate. A new fraction process zone will form in front of the crack tip. So if you look at the fracture from the microscopic perspective, it is a fracture process zone rather than a single fracture. So however, the cracking process of the rock is not as simple as described in the conceptual model. So the main reason is that the rock are natural material with diverse microstructures. So for example, the igneous rocks like granite has a very has the interlocking structure of a uh, different minerals such as the coal, feldspar, and mica, and in sedimentary rocks such as sandstone, the sand grain just compacted and cemented together by the clay mineral. So it is well known that the microstructure affect the mechanical and the physical property of the rock. However, it is unclear that how this microstructure will affect the cracking or the micro cracking mechanisms. So you may ask me why it is important to take the microstructure into account. So in rock engineering, the microstructure of the rock may change in different projects or even in the same projects. So for example, when you are excavating a tunnel, and you may deal with different rocks with different microstructures. And also in the EGS, the thermal microcracks may appear because of the thermal gradients during the heat exchange between the hot rock and the cool water. And also in the CO2 sequestration, which is the hot topic today, the CO2, you may have the precipitation and the dissolution of the clays due to the CO2 rod interaction. So these changes in the microstructure will definitely change the cracking behavior of the rocks. So with this motivation and background knowledge, so I would like to address 3 scientific questions. So the first question I would like to address is how the mineralogy and the grain size of the granite affect this microcracking behavior. So granite is very common host rocks in the EGS, and it is the intrusive igneous rocks formed from the cooling of the magma. And also it is its mineral composition and the grain size distribution depend on the source of the magma and its cooling history, which can be very different from place to place. So to answer these scientific questions, we choose 3 Hong Kong granites with different grain sizes. So the detailed thin section analyses are conducted on these 3 rocks and to quantify their microstructure. So we manually choose the boundary of mineral grains on 5 thin sections and analyze the size and shape of this grain for more the shape and size of more than 1,000 grains. So here are the results, and in terms of the grain size, the 3 granites have very similar grain size distribution, which is a log normal distribution, and the fine, medium, and the coarse grain granites, the grain size, the average grain size is 0.4, 0.9, and 1.2. The medium and the fine grain granite has a very similar mineral composition. However, for the coarse grain granite, this has a more clearspar. So apart from these parameters, we can see that the shape of these grains are generally similar among the 3 rocks. So to investigate the cracking behavior of these 3 granites, we conducted a semicircular bonding test, which has been widely used to measure the fracture toughness of a rock. So in this test, as you can see, a semicircular specimen with 3 notches is loaded under the 3-point loading. As we apply the load, and the cracks will initiate and propagate from notch's tip. And to monitor the micro cracking behavior or the micro cracking process, we use acoustic emission. So in case you are not familiar with acoustic emission, I use this schematics to show how it works. So the basic idea is that the formation of the micro cracking will emit high frequency waveforms, and these waveforms will be detected and transformed into the electric signals by the AE sensors. And here we only draw the 1 sensor for the similarity. So in reality, we have 8 sensors. So these signals are then amplified and filtered by the preamplifiers. So finally, they are digitized and recorded in the AE data acquisition system. So when analyzing the AE data, we first and foremost step is to determine the P wave arrival. So based on the P wave arrival, we use a self-developed MATLAB code to extract the rich information about the AE events, such as the occurrence time, magnitude, or the type of the AE event. So we also apply the thin section analysis to investigate the micro crack features near the notch's tip. So to prepare this thin section, we first glue the various specimen together, and then we prepare a thin section from the center cross section of this specimen. And finally, we digitize the thin section using the microscope under the cross-polarized light. And here are the mechanical and the AE results of the 3 granites. So as we can see that the fine grain granite and the coarse grain granite has a very similar uh, temporal evolution features of A event and energy rates, while the medium grain granite is quite different. As you can see that the duration of the rapid AE development phase, which is phase 3 here, is longest for the medium grain granite. And also during this phase, the AE event rate and the AE energy just increased much gradually as compared with the fine grain and the coarse grain granites. And also we compare the event density contour corresponding to the fully developed FEZ. And as we can see that it is elliptical for the fine grain granite, and it becomes more irregular as the grain size increases. And also we can see that the medium grain granite has the largest maximum A event density, while it is the smallest for the coarse grain granite. So by looking at the thin section of these three granites, we notice that there are more pre-existing microcracks in the medium grain granite. So these microcracks could be reactivated during the loading, and this could explain the different microcracking behavior of this rock. So here are some summary for this part, and we find that the pre-existing microcracks could affect the temporal evolution features of the microcracking energy and microcracking process and the energy release. But however, the grain size and the mineral has an insignificant effect. And also, these three rocks has different spatial evolution features of A events, which may attribute to the different mineral content and also the grain size. So for the second scientific question, we focus on the effect of thermal-induced microcracks. So the topic is motivated by the fact that the thermal cracks may form in granite due to the thermal gradients, which are very common in projects involving some temperature change, such as the EGS. So to answer this question, we choose a coarse grain granite with a few pre-existing microcracks. We thermally treat the specimen to induce the thermal microcracks, control minor. So firstly, we slow heat the specimen into 5 target temperature levels, and then we keep the specimen at the target temperature level for 10 hours. And then we naturally cool down this specimen. So after this thermal treatment, the SCB tests are conducted on the 3 specimens for each temperature group. So here are the low versus displacement result of SCB test for different temperature groups. So we can see as the temperature is lower than 150 centigrade, the low versus displacement behavior of the thermally treated specimen is similar to that without thermally treatment. So the low drops very quickly with a small displacement, which indicate the brittle failure behaviors. And also we find that the number of pre-existing microcracks in this group is similar to the specimen without thermal treatment. So, however, when the temperature is larger than 200 centigrade, the low versus displacement behavior changes. As we can see that the peak load just drop significantly when the load drops and there is a relatively large displacement indicating ductile failure behavior. So I think these changes may be related to the presence of a large number of thermal microcracks. And also we compare the temporal evolutions of the axial load and the AE event rate of the representative specimen from each groups. As you can see, the black color is the load and the blue color is the AE event rate. So based on this, based on their variations, we divide task into 4 phases. And as we can see that the fracture process zone mainly developed during the phase 3. So we focus on this phase, and which is the rapid AE development phase. And as we can see that for the specimen from high temperature group, the phase 3 will initiate or will start at the relatively low temperature, at relatively low load level, and then last for a longer duration. And also its increased rate is much slower than the specimen with the specimen from the high temperature group. So this figures shows how also the AE event density contour of the fully developed FPC. So as we can see that both the dimension and also the maximum AE event density from the high temperature groups is larger than the low temperature groups. So if we look at the variation of the maximum AE event density as the function of the thermal treatment temperature, it just increased significantly as the temperature is larger than 200 centigrade. And the thin section analysis also shows that we have much more microcracks besides the dominant macroscopic cracks in the specimen from the high temperature groups. So based on our findings, we extend the fracture process zone development conception model to describe the fraction process in microcracking behavior in the crystal rocks like granite. So for the granite with a few pre-existing microcracks, the FPC will not rapidly develop until the load reach to a relatively high level. So in contrast, for those with substantial pre-existing microcracks, the rapid development of the FPC will begin at a relatively low level and last for a longer duration, leading to a large fraction process zone with more microcracks. And also, this can be called as the microcracking behavior transition. So the third scientific question we want to answer is how the texture of the rock affect the microcracking behaviors. Here we choose 3 rocks, a sandstone, which is a porous sedimentary rocks, and 2 white crystal rocks, which is the medium green granite and also a fine green marble. So for the sandstone, as we can see, it is the well-sorted sedimentary rocks, and the coarse grain is maintained by some other minerals. And also we can see a lot of pores here, but there are few pre-existing microcracks. And for the granite, it has a very typical interlocking structure, and we can see a large number of microcracks in the green minerals, especially in the cores. For the marble, many consist of the dolomite and the calcite. There are relatively few microcracks as compared with in the granite. So here are the results, and the first column shows the spatial temporal evolution of the AE events preceding the initiation of the macro cracks, and compare with, as we can see that compare with the slight features, the marble, the granite has much more AE events, and for the sandstone, it has the least AE event here. And also, interesting finding is that the distributing pattern of the AE events in the 2 crystal rocks are different from the sedimentary sandstone. So as we can see that the AE event just concentrating in front of the noxious tip, and also the macro crack just propagates through the area with highest AE events. But in the sandstone, the AE events just distribute along the fracture, the microscopic fractures, and also they have different event evolution. Sorry. yeah, they have different evolution patterns. So as we can see that in the granite and the marble, they just concentrate in front of the notch tip, but for the sandstone, they just propagate forward. So to explain the difference in the AE activities, we examine the microscopic features near the notch's tip for the three rocks. So we can see that there are a large number of micro cracks in the mineral grains beside the macro cracks in the granite. But we can see that also the number and the length of the micro cracks in the marble are much less than in the sandstone. And also, as we can see that the cracks in the sandstone just propagate through the cement minerals and cement materials and along the green boundary, and there are very few micro cracks in the mineral grains besides the macro cracks. So based on this result, we can conclude that the most of the AE events in the granites and the marble may be related to the pre-existing microcracks, which are more likely to be mobilized under the stress concentration near the notch's tip. Some other AE events are induced by the nucleation and the growth of the new microcracks. So in contrast, because there are few microcracks in the sandstone, so the AE events are more likely to be caused by the nucleation and the growth of the new microcracks, while the macroscopic crack will subsequently form. So that's the reason why the AE events in the sandstone distribute generally along the macrocrack path. So apart from the distribution, we also look at the fork mechanism of the events. So here we use the radiation pattern method to calculate the fork mechanism and classify the event into three types: the tensile, shear, and the collapse. And it is not surprising that the tensile events are dominant for all the three rocks due to the tensile-induced nature of this test. And it is interesting to see that the granite has the least tensile events, but the most shear events. So you may be curious about why there are more shear events in the granite. So with the help of the thin section, we just measure the angle between the micro cracks near the notch's tip and the maximum tensile stress in our test. So we can see that there are quite a few micro cracks with the angle that's more than 45 degree. So the reactivation of these micro cracks could be the source of the shear events. So here are the summary of these parts. So we can see that the spatial distribution of the microseismic events are highly related to the texture of the rocks. So I think this finding can explain the difference in the AE distribution and their relationship with the microcracks in some other fracture tests on different rocks. As we can see that in this test, the AE events just align well with the fracture in the sandstone. However, in the marble, they do not show a good alignment. I don't think it's because of they don't do the accurate location. I think it's mainly because of the microstructure of this crystal marble. And the second takeaway is the presence of the microcracks will affect the microseismicities. If we have more microcracks, we will have more events because of the reactivation of these microcracks. And also, the shear event may appear and even the tensile loading because of the random distribution of these microcracks. So that's the end of the first part. So let's dive into the second part of this presentation, the intelligent acoustic emission monitoring. So as we know that in the past 10 years, AI has reshaped the world in the way we have never imagined it. So it has become a game changer in the many disciplines, for example, in chemistry and biotech, for example, um, so it can be used to predict the protein structures, so which has been highlighted in this year's Nobel Prize. So apart from the basic science, the AI has also reshaped the solid Earth geoscience. So here are two review papers published in Science that summarize the breakthrough in the application of machine learning or deep learning in solid geoscience. So it has been proved that the AI is quite good at processing large data and extracting useful information from the data. So across the different research topics in the solid Earth, the one that attracts me most is the application of AI in seismologies, because seismology is it's a kind of same phenomenon of acoustic emission, but only in the different scale. So here are two research examples from Professor Greg Rosa's group showing how the AI improved the seismic data processing. So Professor Greg Rosa is the professor in geophysics at Stanford University, and he's also one of the authors of these two science papers. So in the first example, they use the FaceNet, it's the deep learning P and face picking and detecting model to create a new catalog from a ARMA place. And we can see that how the deep learning improves the catalog. And it detects more event and has a more accurate localization because they form a pattern as compared with the standard method. So the second example is they compare the different deep learning associates. The left associate is the unsupervised learning, and the right one is the supervised learning. They prove that the supervised deep learning model can give a good face associate, and as you can see that the A events just align well with the fault that might be in the field. So in view of the breakthrough that AI can make in the seismologies, we ask ourselves if the AI can also improve the A data processing data. So as I mentioned that in the previous slides, the P-wave arrival is a key step in advanced A data analysis, such as the event localization and also the fault mechanism solving. So we use the P-wave arrival time to localize the A events and also use the first peak to solve the fault mechanisms. So to pick the P-wave arrival, both efficiently and accurately. So numbers of automatic algorithms have been developed, such as the ASC and also the short-term to long-term average. However, this algorithm become inaccurate, especially for the low signal-to-noise ratio waveforms. So we're thinking about if we can apply the deep learning model, for example, the FaceNet in processing the A data, because it shows that they have a good performance in picking the low signal noise ratio data. So, however, there are three challenges here. The first challenge is the format of the seismic and the A event data is different. As we can see that the size data has three components and it contains both the P and S wave arrival. However, for the A events, for the A waveforms, we only have one component and only contain the P wave arrival. This means that we cannot directly use the FaceNet to pick the P wave arrival of the A events. So here we proposed our own model, the AEPNet, by modifying the architecture of the FaceNet. So the input of the data is the A waveforms, and the output is the probability of P wave arrival. And the peak of the P wave probabilities will be determined as the P wave arrival that's predicted by the model. So the second challenge is that as compared with the seismologist, our AE community has very limited available data. which is the manually picked data, because the FaceNet or the APNet is a supervised learning. For the supervised learning, we have to have the label data to train the model before we can use it. For example, if you want to predict the shape of this objective, you need to let the model know that what the real shape of the objective is. So seismologists have the lectures of millions of manually picked data to train their face picking model. However, our AE community seldom manually pick the waveforms and share the data. So as you can see that at least only one, the literature that share the data. And also the third challenge is that even we have the open source data, someone may ask if this deep learning model trained by data from one test can be applied to the face picking or the P-wave arrival picking and other tests. So it motivates us to determine what is the minimum number of manually picked waveforms required to train the deep learning model so that we can manually pick a portion of the data from one task and use this data to train the model and pick the remaining. So to address the second challenge is we develop a P-wave arrival picking platform using the MATLAB code. As you can see that using this platform, you can manually refine the automatic picker of the ASA picker, and also you can manually pick your own P-wave arrival. And it has a lot of functions, and you can explore them in the future if my paper is published. So using this platform, we manually pick 50,000 events or the waveforms under their P-wave arrival from track tests on the Berea sandstone. So we will make these open sources, and it will become the largest open data that's contained P-wave manually picks. So with this data set, we can evaluate the performance of the AEPNet. As we can see that as the number of training and validation data increase, the performance, which is the F1 score in this figure, just increase. And then the plateau and at the place when the number of the training and validation data exceeds the 100 and is this the 1500. So this means that the minimum number of manually picked waveforms required to be trained, the AEPNet is 1500. So using the manually picking as a reference, we also compare the P-wave arrival residual from the AEPNet to the ASA picker, which is one of the most widely used automatic picker in the AE data analyze. We can see that the AEPNet significantly outperforms the ASA picker. So we also investigate the effect of the signal-to-noise ratio on the performance of these two pickers. As we can see that when the signal-noise ratio is low, the AEPNet significantly outperformed the ASA picker. As the increase of the signal-to-noise ratio, the difference between the two pickers just a decrease. So we can see how the AEPNet improved the ASA picker. So as we can see, the AEPNet sometimes refine the ASA picker, and also it sometimes also correct the ASA picker both the P-wave arrival time and first peak of the P-wave, and it can also ignore the fake arrival time induced by noise, which is more common in the waveforms that has a low signal-to-noise ratio. So here are the takeaway messages. The minimum number of manually picked waveform is 1500 for training our EPNet model, and we have shown that the EPNet model trained with the minimum number already outperforms the ASA picker, and it has the advantage of picking more accurate P wave arrival, and also to effectively ignore the fake arrival time induced by noise. So in the future, I want to see how the deep learning model could improve the AIC or improve the improve the A data processing like they did in the seismologist. So here is the end of my presentation. So I hope you liked it. With that, I would like happy to take any question. Thank you.
All right. Okay. Thank you. Thank you very much to Dr. Tianyang Guo. It's very interesting topic. Very excellent speak. Now I got one question from the chat. It's asked, yes, I think it's related to your first part regarding the source location accuracy. About the half bazillion test.
Okay.
It says to see events next to the notch. Yes.
Okay. Because I didn't see the, sorry, because I'm sharing the screen, so I'm not.
Oh,
I cannot
let
see
me read.
Okay, I can try to. Not sure on the accuracy of the event location, but interesting to see the event next to notch.
Can I add a little bit to that question that's coming? I think maybe Ed is talking about, and I have the same question, is how accurate are you at locating where these events occur? In order to do that, you certainly need to know the velocity field as well as the timing. And so I think that's the question, is how accurate are you in locating where the events occurred in any of your acoustic emission tests?
Yeah, very good question. So, so in our paper, we have seen our location accuracy, and we use a pencil lead brick test to test the accuracy. So for example, we do some pencil lead brick test. I don't know if you know the pencil lead brick test is just a brick pencil lead at some point before our test, and then we localize those pencil lead brick tests and we compare with and then we do the localization and we compare it with the real all the ground truth location of the pencil lead. And we find that for the sandstone, it has the highest location accuracy, which is 2 to 3 millimeter. For the granite, it has the lowest, which is 4 to 5 millimeter. And also, I think it's because granite has a more, as you know, the low signal noise ratio waveforms, and also in this test we're not using the deep learning picker. We use the ASA. It may have some error in the P wave array picking, as I mentioned in the second part of our presentation. So I want to see that if the deep learning picker can improve the location accuracy, but we in our paper we see the location accuracy. You can, if you are interested, you can read this paper. Thank you. Thank you for your question. Yeah.
Okay, there is, I think it's a comment from the right upper figure on slide 5. Could you please provide the reference for extreme branched out hydraulic fracturing network? There always being a debate on whether hydraulic fracturing grow planar or heavily branched out. Oh, slide 5. I think it's just an illustration. Right?
Yeah. You mean here or the right top figure? And do you mean this figure or yeah,
That is
it's
the
just a
figure I referred
conception.
to. Yes.
Yeah, I don't think it's the real case because we don't actually know what happened deep underground. So we can only use the seismic data to inform the fraction networks. And also I'm not expert in this hydraulic fraction, and so maybe I cannot give a very insightful answer on that direction. But that's my future. I want to collaborate with some engineering, so to discuss more about some results in the field. Okay, I saw third questions. How
Yeah,
do you think the difference in the confining pressure lab experimental versus the field subsurface effect the fraction pattern and how you interpret it?
yes, I think
So
it's an open question.
yeah, of course, the confining pressure will affect, and because the limited of our previous lab, we cannot do the confined fracture toughness test. But I know that in some groups, especially in Europe, in UK, they did some confining pressure. But we also do some traps tests here. As you can see that you can also make use of acoustic emission to detect the A events. I think the one difference in the confining test is it may fail at a very high load level, and also the velocity model will change, and you have to update the velocity model. So I think that's one of the significant difference from my task. And also you may not able to, or not appropriate to use absolute localization method because of the change of velocity model. You can use some relative localization methods such as the double difference, so that you can get rid of the effect of the velocity, and so that you can get a more accurate localization. I think my answer can,
Okay.
can answer your question.
The next question, do you repeat your experiment at different temperature? I was thinking that the anisotropy of rock has a big effect on its fracture toughness. Oh, it's about fracture toughness.
So in our paper, we indeed report the fracture toughness, and as you can see that, as I mentioned, let me see. Here we just report the representative data, but we indeed test the 3 specimen for each temperature group. And for this one, because of limited of our time, and I didn't present all the data. But
Okay.
as you can see that here are some data points. For some groups, we have 3 specimens, some we have 4. And so if you are interested, you can read our paper. And so I think the heterogeneity may have insignificant effect on the results, although it may have some heterogeneity, as you can see that they are quite a large range here. Okay, I hope we answered your question. So very nice presentation. The rock strengths across scales from the micro to max scale. I think I work in the anisotropic rocks and could only hypothesize the phenomena you have shown due to the highly complexity and the variable microstructure. The last steps. I think that's a comment, right?
Yes, I think that's a comment.
Okay.
Okay. Any further question? Yeah, please.
First of all, very nice presentation and nice work. I've looked at myself acoustic emissions in the laboratory, microseismic events from the laboratory, microseismic events from the field. And in all of these cases, this is a stress wave. So it's really measuring stress waves that arrive at my measuring device that I pick up. And so it caused me to think about, well, if it's a stress wave, that means something has to let go, has to break abruptly, very quickly, or you wouldn't create a stress wave. If you have creep and say a microcrack is formed slowly, you have deformation, but you don't create a wave. And so what we're measuring, whether it's acoustic emission or microseismic in the lab or microseismic in the field, they're all stress waves. So I begin to wonder, what's really causing that? I noticed odd things, just as you did in your data. I saw that you see a lot of acoustic emissions, for example, after the fracture has already run.
Sorry, Dr. Green, can you speak a little bit louder? Yeah.
Okay, let me try.
Can you hear me now?
Yeah,
Yeah.
okay.
Yeah, that's great.
Okay. I was asked that question. I was noting that whether it's acoustic emissions or microseismic in the lab or microseismic in the field, those are all stress waves that we're measuring. We're measuring stress waves that are created. Yeah. To create a stress wave, something has to let go or break abruptly, quickly.
Yeah.
If it's creep, you get deformation, but you don't get a wave.
Yes.
If I'm going to create a wave, it has to break. So it caused me to wonder what's causing these stress waves. What does it mean? For example, I've seen, and I noticed in your data, you see a lot of acoustic emissions after the fracture has already run. So you have to ask, well, what's causing that? Now, certainly you'd also ask, could there be a lot of other microcracks formed that don't create stress waves, particularly in the sandstone, where the failures may be more like intergranular breaking the grain boundaries, as opposed to granites and marbles where you're maybe breaking the grains themselves. So my overall question to you is what do you think causes these stress waves? Even though you call them micro cracks, I don't think there's any proof that every acoustic event is a micro crack. What do you really think these acoustic events that you're measuring are telling you?
Yeah, that's a very good question because it's so first of all, we can see the definition of acoustic emission is elastic waves caused by rapid energy release, which is consistent as your understanding is it should be the rapid energy release. And also, I don't think each A events correlate to each micro cracks. I don't think they have the one-to-one how to say the relationship. I think it's a kind of event. There is an event happens. This event could be something like a number of micro cracks. Yeah, I've been thinking about this for a while, but and I don't have the answer at this stage, but I agree that it cannot be interpreted with how many events correspond to how many micro cracks, but it's really a little bit difficult to verify.
I think that you can say, though, it is telling you something.
Yeah, telling something,
you just
but
don't know what it is. I mean, it is an indication of something happening.
Yeah.
And so I think basic research to try to understand, what is it really telling you? What is it really? See, you also get acoustic emission just if you have fluid flow.
Yeah, of course.
And you'd say, hey, why is fluid flowing causing stress waves that you detect? So anyway, again, I congratulate you. Nice work. Good luck in your work.
Thank you. So I can recommend you the paper published on JRL. They summarize some of the source of the acoustic emission. It's not only the micro cracking. It can also have the micro damage when you fracture the surface of a fault, and also the flow rates, as you said, can also cause acoustic emission. But in our test, I think the acoustic emission mainly caused by the micro cracking before the emissions of macroscopic cracks. Yeah.
Okay, Dr. Guo, if you mind, I add something on your response.
Okay.
Okay.
Sure.
Yes. First, thank you for Dr. Edward Barton and Dr. Green. You both initiate a very interesting but literally open topic. And actually, I think once we initiated this discussion, it can last a few hours or even days about this. But we have to end this within 1 hour approximately. And about something, I think something we have overlooked in the question raised by Dr. Green. You said you mentioned about the fracture already go, but the acoustic emission, you can observe a lot of acoustic emission after the fracture already propagating. I think it's a normal observation in laboratory. It's just according to literature, because your loading frame has stored a lot of strain energy, and once it cannot sustain, the sample cannot sustain, it's just release energy, and the energy release is exponentially increased. And the second, about the anisotropy rock hypothesis, like Dr. Edward Green mentioned, he hypothesized the phenomenon is just due to the high complexity. Actually, when I listening to this webinar, I also think about this point. Yes, in principle, I agree with Dr. Green's suggestion. You know something happening, but you don't know exactly which correlated which. But maybe in the future, say, like Tianyang, you presented micro scale observation on the grain and its distribution and et cetera, right? So maybe if we happen to find some ratio between the pre-test observation and the certain AE feature, and it may have some evidence or have some trace about which to which. Like if this ratio between different set of data can persist across different type of rock and different type of test. So it's just some hypothesis. Okay. Anyway, we have to end this webinar very soon. Yeah.
Yeah, thank you. Thank you again for inviting me to have this engaged discussion, and I hope you like it. And so if you are interested, you can reach out to me either by my email or linking, and then we can have a further discussion. Thank you.
Yes. Okay, thank you. Thank you for the speaker, and thank you for every attending. Thank you for the very insightful question. So Dr. Wei, if you have anything before we end this session.
No, this is really informative, and I really enjoy this discussion. And our next webinar is on the 13th of December on Friday. It was during AGU, but I hope everyone will still attend this webinar. We'll see you next time.
See you. Bye.
All right.